we're now going to go into homogeneous nth order constant coefficients. So we're trading some difficulty in order n, while also staying in a linear setting. In the constant coefficients, we're always looking for non-trivial solutions, and we're going to stay in the homogeneous area. So the first thing we're going to look at is how you can write these things down. So if y is a function, the only way you can have a linear high-order constant coefficient ODE is by having a sum of terms in which you have a being a constant and y parenthesis I being the ith derivative of y. So in this formula we have, starting from the right, a0y, then a1 y prime, and so forth up to order n. I will associate to this equation a characteristic polynomial. That really means, practically, that I'm going to replace y at the ith derivative of y by the ith power of lambda, where lambda in this case is a number. And I'm going to take these ansatz, this first guess on the shape of y. I'm going to say that y is going to be a constant times an exponential with power lambda x. The very nice thing about exponentials is that taking derivatives of them is extremely easy. So if I know that y has this form, then I also know all the derivatives of y very easily. If you want to do it by hand, you can prove that, well, y prime of x is c lambda e at the lambda x, y second of x, sorry for the typo, is equal to c lambda 2 e at the lambda x, and that goes on where the general ith derivative of y is the same c constant, lambda to the power I, exponential of lambda x. So if we're looking at our ODE, and we take this assumption on the shape of y, we can replace all the derivatives of y by the derivative we just computed. Now, if we we know that the exponential of lambda x is non-zero, at least for some values of x, actually for almost all the values of x. This is pretty good because then we can divide by e at the lambda x. We can also divide by the constant that we assume to be non-zero, so we get back to actually having the characteristic polynomial I just introduced. And the claim is that the solutions of the characteristic polynomial allow us to construct the solutions of the ODEs because they feed back into the ansatz that I just created. Furthermore, there is a theorem that if y1 is a solution to a homogeneous ODE, so is any multiplication of y1, and if y1 and y2 are two solutions of a homogeneous ODE, so is the sum of the two terms. This is true only for homogeneous ODEs, not in general. But that means that we can easily construct new solutions if we already have the building blocks. Just to point out, C1 y1 plus C2 y2 is a new solution, that is a solution that we haven't found before, only if y1 and y2 are linearly independent. That means you cannot construct y1 as y2 times something. And exponentials with different exponents have this property of being always linearly independent. So we have drawn a relationship between the ODE and the algebraic equation that I call the characteristic equation. And with the theorem we just saw, if lambda j's are solutions of the algebraic equation, then the sum of Cj being constant, exponential of lambda j x, is a solution to the ODE. So we are summing all the exponentials of all the solutions of the algebraic equation that we have found. And we are thus creating a solution to the ODE. Let's look at some examples of this happening. Let's take this second order, the ODE in y. It's linear, it's homogeneous. We can apply what we have just learned. So we're going to construct the characteristic polynomial. So you see that the structure is exactly the same. I'm just replacing y with lambda and derivatives of y with powers of lambda. That means that the third term, minus 3y, gets replaced by 3 lambda. 3 without a lambda. Because there is no derivative of y, that means that there should be lambda to the power 0. This lambda second plus 2 lambda minus 3 is a second order equation that we can solve by hand. You can use whichever method you want. And we can find fairly easily that the two solutions of this second order equation are lambda equals minus 3 and lambda equals to 1. By what we have seen before, that means that there are two partial solutions of the ODE coming from the two solutions of the characteristic polynomial that we have just found. We have a first block being exponential of minus 3x and the second block being exponential of x. And then we combine the two, we sum the two, and we multiply each of the two terms by a constant that we don't know. So this is the general solution for the ODE. Let's check if what we have found actually works. Well, for the exponential of e of x, that goes very easily because we know that whatever derivative of e of x is itself, so we can do the computations fairly fast. And we can see that indeed when we plug in c2 of e of x, the solution is straightforward. For e at the minus 3x, then we have to be a bit more careful calculating the derivatives. But if we plug it in, we have e at the minus 3x appearing 3 times. We don't care about that term, we just have to check that the coefficients in front sum up to 0. So we have 9 plus 2 times minus 3, that comes out to be actually 0. So yes, the thing we found is indeed a solution. The second example I want to look at is this third order equation in y. We construct the characteristic polynomial exactly as we did before, and we try to find a solution to a third order algebraic equation. You can find out that you can start by noticing that lambda equals to 2 is a solution to this equation. Then you can divide your full left-hand side by lambda minus 2. Just to remind you how that works, this is one of the many ways you can solve a third order equation and one of many ways you can calculate a division between two polynomials. You can see how many times lambda minus 2 fits into lambda to the third minus 8 lambda plus 8. And you start by noticing that in order to get rid of the highest term, you need to multiply it by lambda 2. So here you have minus the polynomial lambda 3 minus 2 lambda 2. And you do the difference between the first and the second line. You retrieve something, and you wonder what is the value that would allow you to get rid of the highest order term. Turns out that is 2 lambda. So this is a mistake in the slides. If you multiply 2 lambda by lambda minus 2, you retrieve something that 2 lambda squared that allows you to get rid of the first term, and 4 lambda that allows you to get rid of 4 lambda out of the 8 lambda that you have. And then to solve for the last equation, you need minus 4, and that indeed solves it exactly. So we can rewrite our algebraic equation as a multiplication of 2 lower order terms, and by straightforward second order formulas, you can find that the second and the third root are minus 1 plus or minus square root of 5. then the partial solutions of the ODE are, well, exponential of 2x, exponential of minus 1 plus square root of 5, all of it multiplied by x, and exponential of minus 1 minus square root of 5, all of it multiplied by x. And we can just write the general solution of the ODE as the sum of the partial solution, each multiplied by their own constant. Let's look at what we have found until now. So we have a second order equation that we can solve and find a sum of two simpler solutions. So we need two conditions to fix C1 and C2. Then we have looked at a third order problem that sprouted three unknowns, C1, C2, and C3. This is a general pattern that we can turn into a theorem if you have a homogeneous ODE, linear. It needs n conditions to define a unique solution. So in order to get rid of all the coefficients that are unknown in your general solution, you need some either boundary conditions or initial conditions, enough of them to have enough information about where your function lies.